The OMOP Concept Mapper is a tool that automatically translates any term from a hospital's electronic health record system into the standardized OMOP Common Data Model vocabulary. It uses a large language model to understand and interpret medical terms, like long COVID or test for creatinine, and find their closest standardized matches in OMOP. The system works in 4 stages, each adding more structure and precision to the mapping. Stage 1. Concept expansion. The system starts with a raw input term, for example, long COVID or test for creatinine. The generative AI model expands on this term by doing the following: writing a short description of what it means, suggesting ancestors or related categories, for example, COVID-19 related condition, creating a harmonized version of the term that looks more like how OMOP concepts are named, for example, post-acute COVID-19. This harmonized term helps the system find better matches later on. Stage 2. Semantic retrieval. Using the harmonized term, the system searches a database of OMOP concepts to find the most similar ones. It retrieves a user-defined number of candidate concepts, for example, the top 10 or 20. To improve understanding, it also looks at the knowledge graph of OMOP concepts, exploring each candidate's family tree, parents, siblings, children, and related terms. Stage 3. Concept filtration. Now the system cleans up the results. It reviews the original input, the harmonized version, and the retrieved candidates to filter out irrelevant concepts. The goal here is to remove noise, keeping only the terms that truly match the meaning of the input. Stage 4. Concept selection. Finally, the model chooses the best possible match from the filtered list. It also gives a short justification explaining its reasoning, a confidence score for how sure it is, supporting details like synonyms, ancestors, vocabulary type, and domain. Before typing in a medical term, I'll walk through a few of the configuration options on screen. First, the language model. This pipeline can work with any LLM you prefer, commercial ones like Anthropic, OpenAI, or Gemini, or open-source models that you might run locally. For example, at NYU, we could use NYU Tron, and at Montefiore, we often use Albert LLM. For this demo, I'll go with Anthropic. Next is the domain filter. If you already know which part of the OMOP model your term belongs to, for instance, a lab test, a drug, or a condition, you can use this filter to limit your search to that area. This helps speed things up and improves accuracy. Then there's graph rag breadth, that simply controls how many potential matches the system looks at before narrowing down. A higher number means the system explores more options, but it takes a bit longer to run. All right, let's try an example. I'll start with long COVID. I'll just type that in and hit map. The system now runs through the 4 stages we talked about earlier: expansion, retrieval, filtration, and selection. It takes a few seconds to finish. And here's the result. The system matched long COVID to OMOP concept 705076, post-acute COVID-19. If I click on alternative labels, I can see the synonyms it used, as well as its ancestor concepts. It also shows details like the domain, vocabulary source, confidence score, and even how long the process took. Let's peek behind the scenes a bit. In Stage 1, the system took long COVID and expanded it, creating a short description, identifying possible parent concepts, and generating a harmonized name to help find better matches. That harmonized term is what it used in Stage 2, the retrieval step, to search for similar OMOP concepts. Since I set the graph rag breadth to 11, the system pulled in 11 possible matches. Then it filtered out the weaker ones, leaving us with 5 strong candidates. Then, in Stage 3, it picked the best overall match and explained why that one fit best. If I scroll down to the debug view, you can actually see those 11 candidates, each with their metadata: name, domain, vocabulary, class, synonyms, and relationships to other concepts. That's the information the model used to reason through which one to choose. Let's try another one. Test for creatinine. Here, I didn't type the exact medical term, just a short description. The system mapped it to creatinine mass over volume in serum or plasma. That's a good general match since I didn't specify what kind of test it was. If I had said serum creatinine test, it would likely have chosen a more precise concept. Again, we can see the synonyms, ancestors, and an explanation for why it selected concept 3015160. In the background, the generative AI model understood test for creatinine as a lab test that measures creatinine in blood or urine, then harmonized it into a form similar to the OMOP label before matching. Let's do one more, HbA1c. This time I'll set the graph rag breadth to 20, so it explores more options. It takes a few seconds longer, and now we get the correct match for the standard HbA1c lab test. Clicking on it shows its alternative labels and ancestor concepts, and if you click the link, it even takes you directly to the concept in Athena. In practice, you can use this interface interactively like I'm doing now. Just type in a term and get the mapped concept, or you can run it automatically in bulk. That's how it's typically used, to auto-map local electronic health record data to the OMOP Common Data Model. It can also support clinical trial matching, where inclusion criteria are written in plain language, like patients with elevated creatinine, and the system automatically identifies and maps those terms to OMOP concepts. So whether you're standardizing data, matching trial participants, or just looking up a concept name, this pipeline can handle the mapping automatically and accurately.